In this video tutorial, I will briefly demonstrate a few ways of storing and accessing two-dimensional data in Python 3. The most straightforward way is to store the data in a matrix made up of nested Python lists. If you know the data beforehand, it is easy to hard-code it directly. So I can store a list of lists 1, 2, 3 and 4, 5, 6 and 7, 8, 9. The outer list essentially stores a list of rows. Let's copy this to IPython. I'm starting IPython 3 here and can paste the text here using Ctrl-Shift-V. And this is my matrix. You can have a look at it. Python will represent it here as a list of lists, because that is what it essentially is. If you want to print it slightly more comfortable, I can say for row in M print row. That will print each row on a separate line. There we go. You can access the data just as we would access it in lists, but this will return me the whole second row. If I want to access an element in the second row, I need to do it like that. Of the second row, give me the last element. And it's 6. You can also change this value, say to 0, and now this value is changed. You can also perform inline calculations. I can do for row in matrix, for index, comma lm in enumerate row, and let's say we set each value to its square, so the index row at index is lm squared. And let's have a look here. And 4 is the square of 2, 9 is the square of 3, 16 of 4, and so on. I'm cleaning the screen here with Ctrl-L. If we do not know our data beforehand, we may want to initialize a matrix of, say, zeros or of any other values. I'm picking a dimension here, let's say 10. If I want to initialize a matrix, I first have to initialize the rows. Let's say each of the rows should be full of zeros. And how many zeros? Well, the number of dimensions. So my row is now here 10 zeros. I can initialize the matrix and say for underscore in range dim. What does this mean here? It means ignore the values that I get from this function. This function will simply iterate 10 times, and I'm ignoring the counter from 0 to 9. What am I doing? I'm appending to the matrix the row we just did, but I say list of row. Why am I doing this? Because otherwise I will have 10 times the same reference to the same row. That means I'm not having a matrix of 10 different rows, but of 10 times the same row. I'll show the effect of this in a moment. So here we have a matrix of 10 rows and 10 columns, and we can access it. Let's say pick this field here and set it to 1. Let's have a look. And this field here is set to 1. If we wouldn't have been careful and initialized the matrix with copies of the rows, so I'm doing the same again here, for underscore in range of dim m dot append l. Note here I forgot not l row. Note here I forgot to use the list constructor, so I'm using the same reference over and over again. And if I now say m at the index 3, 7 is 1, I'm setting the 8th element of the used row to 1, but since I have the same row reference over and over again, all of the rows will be affected. So this is not what I want. So to properly initialize the matrix, do not forget to say append list of row to get a copy of the row. Good. Besides using matrices in this shape, list of lists, you may want to represent data tables like this here, where this data here is associated with its title, Pat, and this data here is associated with the title column, Chris. To do so, we can have a list of dictionaries. Each row is an element of the list, and each of these rows is realized as a dictionary. Say the value 12 is in the first row here, and it's associated with the key Pat. The 17 is associated with the key Chris. Let's copy this to IPython using Ctrl+C and Ctrl+Shift+V. And if I want to add a new line, say here I forgot this, I'm saying m.append, and we'll add a new dictionary now with Pat and the value 28 and Chris with the value 23. My matrix is now having this fourth line as well. I can of course access the values straightforward as you would expect it, so I can say m take line 3 and say tell me the value that Pat had. It's 21, or set this value to 18 instead. We can have a look, and the value has been changed. Say these are scores of a sports game Pat and Chris played together. Now I can iterate over these scores to get some result table. I'm cleaning my screen using Ctrl+L and type for a row in my matrix. Let's say if Pat won, if row of Pat is greater the value of Chris in any row, then well obviously Pat has won, so print Pat won. If however the value of Chris is greater, that means Pat has less, then Chris won. And in all other cases we have a tie. And there it is. Chris won because here 17 is greater than 12. In all other cases here Pat has won. We can combine dictionaries and lists as you please. Here we've created a list of dictionaries. It's also possible, however, to create a dictionary of lists or a dictionary of dictionaries. Let's have a look. If we have a two-dimensional table having both column headers and line headers here, we may want to mark both the columns and lines with specific keys. We can do this here. Let's say we create a dictionary full of lines as keys, 2012, 13 and 14, and the values are again dictionaries with the column values. Let's copy this into IPython, Ctrl+Shift+V, and we can access this sales data as you would expect, 2013, second quarter, and we get the data. We can also overwrite the data and change it just as we please. So far we have seen how to store and access two-dimensional data by simply combining Python lists or dictionaries. However, if you want to perform calculations on your 2D data, the best option in Python is to use a third-party library called NumPy. NumPy not only allows to easily create and modify 2D data, but also performs much better when doing calculations with these matrices. The best thing about NumPy is that it is open source software and can be freely used for essentially all purposes. In terms of speed, it performs just as well as the best proprietary programs for matrix manipulation on the market. To use NumPy, you need to make sure it is installed. The installation procedure is particularly easy on Debian or Ubuntu-based Linux systems. If you're lucky enough to work on one of them, this is how you install NumPy for Python 3. I will leave the IPython shell here now using Control Z, so it's put in the background, and I can do this as super user, use the program apt-get, which downloads, installs and configures software. What I want to do is to install software. I want to install the package python3-numpy. I need to add my credentials to be allowed for installation as administrator, and I've already installed the package, so apt-get says it's already there. Otherwise it would be installed by now. I now use the command fg for foreground to foreground my IPython3 program, the already existing session. To use numpy, I say import numpy as np. Just for convenience to have to type a little less, now I can say np constantly. If I want to create a zero initialized two-dimensional array, I can say np.zeros of 3, 4 and get a 3-row 4-column array. Or I can do a one initialized one saying np.ones of 4, 3. Let's print this, and here I've got 4 columns and 4 rows and 3 columns. Be aware that NumPy doesn't use the same behavior as Python lists when performing basic operations and using slicing. I'm cleaning my screen using Ctrl L. Now I say a plus a, which does not concatenate the matrices together, but it adds the matrices values, so we need the same dimensions. Or we can say 3 times a. Now we'll get a matrix full of 3s. If we want to do matrix multiplication, we can do this as well. So far we've been using NumPy arrays. NumPy arrays are very powerful. Let's say a dot. They have plenty of functions we can use them for. But here we can transpose them, but we have no option of inversing them, and we cannot do matrix manipulation directly. Instead, we need to have at least one matrix as part of the multiplication. If we want to create such a matrix here, which is essentially a range of values from 0 to 7, or this here from 0 to 19, we can use the arange function. Let's have a look. Arange of 20 will result NumPy, not a, I'm sorry, this is np.arange of 20. This will create a one-dimensional array with 20 values from 0 to 19, but it doesn't have the correct shape. What we want is a reshaped np.arange of 20, and it should be reshaped to 4 lines and 5 columns. Let's have a look here, and that's what it is. You can also access the single values as we already used to. Let's say the fourth value in the second row, that would be 8 here. There's also a slightly simplified syntax for NumPy. You can say 1, 3 to also access this element, and it still works. Now let's create a matrix, because this is just an array and multiplying arrays directly is not possible. Creating a matrix is done, not hard to guess, using the numpy.matrix constructor, and I will initialize it here with an arange of values up to 8, so from 0 to 7, reshaped to 2, 4. So this is essentially then this matrix here, from 0 to 3 and from 4 to 7. Now I can perform m times a, which is the matrix multiplication we've seen here, this matrix times this one here, and since this is a 2 times 4 matrix and this is a 4 times 5 matrix, the result will be a 2 times 5 matrix. And there it is, a 2 times 5 matrix. Let's see have a look at what we can do with matrices. M dot, and I use the tab key for auto-completion. And there are even more functions here available for use with matrices. We can, for example, transpose the matrix, or calculate its inverse. M.T, that's the transpose matrix, and M.I is the inverse of a matrix. Showing more details about NumPy is beyond the scope of this introductory tutorial. If I whetted your appetite, simply have a look at the tentative NumPy tutorial. And the tentative NumPy tutorial can be found using your favorite search engine or directly accessing it at wiki.scipy.org/tentative NumPy tutorial.